thank you. So I'll just, for the sake of people who will watch the recording, I'll just simply run through what we have discussed till now. So we are talking about a wide sense stationary information source xn that is highly correlated with its sparse values, and assuming that xn comes from a Gaussian distribution, that we want to allow not more than a fixed amount of quantization noise, which is given as this delta square by 12, means that the number of levels required is proportional to sigma square, since sigma is a measure of the variance, or sigma is a measure of the spread of that Gaussian distribution. So uh, the more the spread, the larger number of quantization levels that you will require.
Sir,
Yeah,
can you please
Suraj.
reshare your
Yes,
screen? I'm
yes,
unable
yes,
to.
yes, Suraj. Doing that. Okay.
Both
Adit, can you
Ashish?
please mute yourself? Hmm? So, ah, OneNote crashed. Did it? Yes, it didn't, thankfully. Yeah, so the number of quantization bits is proportional to log to the base 2 sigma x square. Fine. This you will eventually know to be differential entropy. So this I leave on to the information theory course to introduce you to differential entropy. But
Sir, the screen is stuck. Yeah,
sorry,
now it's okay. Yes, yes, it's
yeah,
okay,
it's
sir.
okay now. Yeah, yes. So the number of levels required is proportional to sigma x square, and the number of quantization bits is so in other words, the larger the variance of the random process to be coded, the more bits have to use. And since the more quantization bits will be required, so we will need higher rate of communication, and we will also require more storage. Agreed?
Yes, sir.
Yes. So, but we said that xn is highly correlated. Means RK, since this is wide sense stationary, right? Now, what is the physical significance of correlation or physical meaning of correlation? It means that when we say that two random variables are highly correlated, means that so correlation means that if I have xn minus 1, xn minus 2, and so on, then xn will be close to these, right? Is this what correlation means? Or in other words, can use xn minus 1, xn minus p to predict xn. Can we not say this? Say, we know that the temperature taken every second is highly correlated, or taken every minute is highly correlated. So if the temperature inside my room right now is 18 degrees Celsius, you can say that within the next 1 minute, the temperature will lie between, say, 17.5 and 18.5 degrees Celsius with a lot of certainty, right?
Yes, sir.
Yes.
And if we even know that the temperature increases during the day and decreases during the night, then if I give you the time series data where the temperature has been increasing, say for the past 15 minutes, you know that temperature is increasing, then you might also say that in the next instant the temperature will increase. Or if the temperature right now is 18 degrees Celsius, then maybe 10 minutes later the temperature will be between 18 degrees Celsius and 18.5 degrees Celsius. You can say that.
Yes, sir.
So correlation, whenever we have large amounts of correlation, it can be used for prediction.
Yes,
Or
sir.
if I have highly correlated past values of xn, then I can use those to predict xn. Agreed? But we cannot pinpoint. We know that. So I can write that xn can be written as a linear combination, say k equal to 1 to p wk. This conjugate, you will know why. You will know in 5 minutes why I'm using this conjugate. Right? I can write xn as a linear combination of its past values using p past values. Say I say
Yes.
that I can use the p past values of xn to predict its present value, then I can write xn, the present value of xn, as a linear combination of its p past values. Agreed?
Yes.
People accept Rahul because Rahul has read another book that I recommended. So uh, I need
Sir,
other people to understand this as well. Yeah.
Yes, sir.
uh, WK is the vector conjugate complex conjugate vector.
Ha- where do you see a vector? Have I defined a vector?
No.
Then how is this a vector?
Okay. Okay.
We'll come to vectors. naturally, but
Sir, what
we'll
is
eventually have to
WK?
resort to vector notation. But so now is another interesting part. So you can use the past values to predict the present or the future, but we never know what the future exactly will be. I can say that the temperature will lie between 18 degrees and 18.5. Okay, Kirti. So explanation for what, Kirti? If you can pinpoint me to that, it'll be helpful. WK is a scalar, or WK is, so these are weights, or WK. So rather, I would put it this way: if Xn can be represented as a linear um, predicted nation of its past values, then WK conjugate is the weight assigned to Kirti. Is this fine? Yeah. So now we come to another point. You don't exactly predict the future. You say that the temperature 5 minutes later would be between 18 and 18.5 degrees Celsius, but you cannot say that it will be 18.2. There's always that some uncertainty left, right? And it is that uncertainty that contains all the information. You can most probably predict what the next sentence that I am going to say, what I'll say is going to, or what the next word in the sentence that I'll say is going to be. But it's, there is something that and the information is highly correlated. That information that I'm conveying is highly correlated. I say the word correlation again and again. You know that I'll use the word correlation a lot. That you can predict, but where and how I will use this correlation is unknown. So there is a lot of things. So based on the past samples, a lot can be predicted, but there is still something that you don't know, or there is still some information left. So if we can exactly predict this from its past values, then Xn contains nothing new, no information as compared to the past. Do we agree on this?
Yes, sir.
Yes, sir.
Yes. So now the next postulate, that if Xn can be exactly written in terms of its past values, then Xn is not required. The past values are right? So therefore xn is actually or the present is a mix of the past plus something new. Fine. This is eta n
So,
is uncorrelated with and is fine. So this new, what is new is not dependent on the past and is itself temporarily white, or you can say is a white noise process, whichever nomenclature you prefer. So this eta n is called the innovation component. The component which is unpredictable, which is unknown, and since it is unpredictable, you don't know what will it be. So this is what differentiates the present from the past and the future from the present. You can obviously construct a philosophical discussion regarding this, but we are focusing more on a mathematical discussion and not on a philosophical discussion. So xn or any information signal, correlated information signal, can be represented as of its past and an fine. So I write is this fine?
Sir,
Yeah, Ajit?
the value of P that we take, is
Yeah.
it already known to us given a channel, or do we calculate it somehow? Bec-
Uh, that discussion possibly at the end of your you can do a PhD on that, honestly.
Sir,
So yeah, right now
sir,
we assume that this P is known for simplicity. Yeah,
Okay,
Shubhashish.
sir.
sir, that weights are that known to us, or we again find it?
That you will know by the end of this class.
Okay, sir.
Okay. So this. So this is a representation actually, or this is the case where we. So no, assuming that these weights are known is for physical modeling, and we need to calculate these weights for practical purposes. So anyway, so now right, agreed or
Yes,
not?
sir.
Yes. So
Sir, excess of complex valued.
yeah, we for the general for the sake of
Okay, sir.
generality we take x to be complex valued.
Okay, sir.
Okay, because we derive it for real value, then you have to do extra work to make it complex valued. But if we and deriving it for complex valued systems is not that hard if we start off with complex valued. So let's do it for the complex valued case directly. Right. So now taking expectation on both sides. Expectation, 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 expectation. We see that these two terms directly go to 0 because we have already said that this is 0 for k greater than 0, and these are for k greater than 0. So the last two terms directly go to 0. Okay. Guys.
Yes, sir.
Sir,
Yes, sir.
Yes,
So the
sir.
Yes,
last two
sir.
terms go to 0. We agree on that.
Yes, sir.
Yes, sir.
Yes. So, We'll be taming a lot of beasts today. This beast, fine.
Yes, sir.
So now, since this is a square of a summation, right? This I won't explain this. You figure out yourself that if I square a summation, it becomes a double summation. I leave this as a self-study exercise. As a hint, uh, a plus b, or if a plus b, if I write it as summation of I going from 1 to 2, then the square is basically double summation ai aj, both I and j going from 1 to 2. Agreed?
Yes,
Yes,
sir.
sir.
Yeah, so that
So,
you can use induction possibly to prove this yourself.
sir,
Yeah.
the expectation of innovation part will be there, right?
Yes.
Okay.
Fine. So this
Yes, sir.
summation k equal to 1 to p, l equal to 1 to p, wk conjugate wl, expectation of x n minus k n minus l r of l minus k. Right?
Yes, sir.
Yes, sir.
Now, equivalently, let's leave this equation here right now, and equivalently invoking the vector notation. Xn equals right? Fine.
So it was a double summation, right?
No, double summation was this when I took the expectation or when I took the expectation of the square. This is this.
Okay, okay. And what happened to the RL minus K?
No, that's what I'm saying, that let's leave that equation aside for now. I'm deriving the same equation in vector notation.
Yes, sir.
Sir, the xn is a zero mean
Yes,
process.
we, unless stated otherwise, everything is zero mean.
Okay, okay.
So this is an equivalent, xn is an equal, this is an equivalent representation of this. Fine.
Yes, sir.
So this now xn, yeah, this one. So now fine, where A Hermitian B equals A conjugate transpose B and A Hermitian B conjugate equals A transpose B conjugate equals B conjugate transpose A equals B Hermitian A. Fine.
Yes, sir.
Yes, so sigma x square is this, or since W is or W's are constant, equals expectation W Hermitian expectation of x n minus 1 x Hermitian n minus 1 W plus right.
Yes, sir. It's a
Yeah,
linear operation, sir.
yeah, right. So this now xn, or I'll write xn for a reason. Since this is wide sense stationary, I can get rid of minus 1 in both. Equals xn minus 1. So these are conjugates.
Sir,
Just a second. Yes.
that vector, won't it be till n minus p plus 1?
Yeah, and minus p plus 1. Sorry. Thank you. P plus 1. And
Well, uh, so shouldn't it start from x of n minus 1?
I just said that since these are Whiteson stationary, we can replace, we can get the index, we can change the index without any problems. Just that we
Okay.
have to be consistent with the length.
Okay.
Again, invoking Whiteson stationarity. This is expectation. So for this matrix, I take the expectations of individual values. I can take the expectation of the matrix by taking the expectations of the individual values, right?
Yes,
Yes,
sir.
sir.
Yes. So this becomes R0, R1, Rp minus 1, R conjugate of 1, R0, R conjugate of P, R0. Right?
Yes, sir.
Yeah. So this is called the pth order covariance matrix of Xn. Okay, this is a name. So R equals expectation of Xn, Xn. And obviously, since this is Whiteson stationary, it won't matter. I'm omitting the order P because it soon turns ugly. Fine.
Yes, sir.
Yes. So, and this pth order covariance matrix has a few properties that are of interest to us. One, for or for Whiteson stationary random processes, this covariance matrix, this has following. One, it is Hermitian symmetric. So which means that R Hermitian equals R. One, two, it is histopletes. That is the elements on all the diagonals are the same. You see that the elements on all diagonals are the same. So this is a this is a Toeplitz matrix. 3, it is positive. It is positive semi-definite. What is positive semi-definite?
Eigenvalues are greater than or equal to 0.
No. That is a consequence of positive semi-definiteness. Positive semi-definiteness A is or X contained in RP in this case for all, or CP actually, not said to be positive semi-definite if for all X in the p-dimensional complex space X Hermitian X and it is said to be positive definite.
Sir, X conjugate, since X
X
is a
Hermitian.
sir, X is a vector, right?
Yes, X is a vector. Hermitian. X Hermitian AX.
Sir.
Sorry?
I was saying yes, sir.
Yeah. Bhavnik, okay?
Yes, sir.
Yeah. So said to be positive definite if the equality is satisfied only if fine. So based on this, now let us revisit the equation above and we see that sigma x square equals W Hermitian RW plus sigma eta square. Right?
Yes, sir.
Yes, sir.
Yes. So if in general right, or quantize eta x, we can get away using smaller number of quantization. We can get away using a smaller number of quantization levels.
Yes, sir.
Right. So this is called predictive coding, and the overall scheme is known as differential pulse code modulation. Fine. But to
Yes, sir.
implement this practically, need to know sorry, not this. To implement this practically, we need to know W1 to WP.
So basically the weights, right?
Yes, we need to know to implement this practically, because we'll have to extract the error, or you can what you are doing is what you are basically doing here is that you are predicting xn, and xn basically you are writing as xn equals x hat n plus eta n, where x hat n is the predicted value and eta n is the error, and you are quantizing and transmitting the prediction error, right?
Yes, sir.
Because it's useless to transmit what you are what you can already predict. Great. So we'll stop here, and tomorrow we'll discuss how to extract or how to optimally predict this so that we get maximum advantage. I hope that's okay.
Yes, sir.
Yes, sir.
Okay then. Bye. Have a nice day.
Bye, sir.
Bye, sir.
Right, sir.
Bye,
Thank you,
sir.
sir. Bye, sir.